7T on our head-only system, and now we've been moving on to doing things on our 3T as well. And I'll just give a tour of what we've been up to. So, but first I should start off introducing where we're from. So I'm at the Center for Functional and Metabolic Mapping. Rabbi was giving me a hard time because I didn't have that in my bio on the website. So, but here it is, front and center. But so yeah, we're located here. We're actually, even though we're in Canada, we're actually located south of where we are right now, where it dips down there close to Michigan. And we have 3 scanners right now. We have another one, well, it says coming early 2024, but that one is actually going to arrive in November, and then it should get finished installed by early 2024. So what we have is a 3T Prisma, that's a whole body system. We have a 7 Tesla Terra Plus head-only system. We have a 9.4T Brooker Neo for small animals, and we have a 15.2 Tesla Brooker Biospec coming, and that will be used for mice. So in my lab, really the overall arching goal for me is microstructural MRI with applications to neuroscience. So you'll be seeing lots of pictures of brains in this talk. So it's nice that Paul showed you something outside the brain before this. And really my expertise is on technical development. That's kind of the core talents that we have in my lab. And then we work with others in collaborative studies to take those technical developments and learn more about the brain in both animal models and in patient studies. So the field probe system is more on the development side. We're moving on to more applications these days, which I'll tell you about. But just to give a brief intro to the motivation why we're interested in field monitoring in my lab is that we're interested in characterizing microstructure, and to do that, diffusion MRI is really powerful. The problem with using advanced diffusion MRI methods is they require really long echo times. And at ultra-high field, you get a little bit of a shorter T2 time, so those long echo times make things even worse if you're at higher fields. So we want to go to single-shot spiral to get that large decrease in TE that Paul was already talking about. So I have basically the same plot that he showed, where you can see that so EPI is shown in the upper right quadrant there, and spiral is shown below that. And since you start at the center of K-space with spiral, you save a lot of time in terms of your echo time. It's also relevant that you save time not just where you have that EPI train. Actually, let me get my cursor here.
I think off to the right, you have to move it.
I got it. There we go. So over here you have this time you save just from your EPI getting to the center of K-space, but you also save that time on the other side of your 180 as well, because to keep the echo times the same on both sides of your 180. And this actually has a huge impact on SNR. So this is just some back of the envelope kind of calculations for SNR improvements for both 3T and 7T for spiral relative to EPI. And this is just using T2 times from the literature. And it gets better, the improvement is higher as you go to smaller voxel sizes, just because it takes more time to get to the center of K-space for your EPI train. So at 3T, if you have kind of low resolution, you're at about, from 1.4 to 1.8 factor improvement, and that actually lines up really well with what Paul just showed in the prostate. But as you go to high resolution at 1 millimeter, you get a 2.5 factor increase for spiral. And then at 7T, that increases to a 4x increase for those high resolutions. So that's like a 16 factor of time savings. So it really becomes worth it though. But the reason everyone's not using spiral for diffusion MRI is obviously, I'm kind of preaching to the choir here, but it's because of eddy currents. So non-Cartesian MRI is really strongly affected by eddy currents. So to demonstrate that, I just have this little cartoon here. And this, on the upper right, is a diffusion sequence that this was with spiral, reconstructed using our homebrew recon with the scope system information. And then the bottom here is ignoring the diffusion gradient eddy currents. So this is where, if you just use the the scope measurement from the non-diffusion weighted image and apply it to all the diffusion weightings, you can see that you get blurring because of those gradients. So with EPI, you get these distortions that you can correct. People do that all the time with FSL eddy. But with spiral, you get blurring, which is a lot more difficult to correct after the fact. So that's our motivation for having the scope system, because if you didn't have diffusion gradients, you can actually do pretty decent by just getting your delays right on your spiral. That's half the battle. But once you start adding in these long-lasting large eddy currents from the diffusion gradients, it gets pretty problematic. All right, so with that introduction done, I'll be talking about some progress. And this is basically a whirlwind tour of the publications we've had in the last few years. So this is the stuff that's kind of complete. And then I'll talk about current work, where are we going now, and then I'll just finish with some outlook on some things I think will be important to look at moving forward. So one thing I'll just highlight is we do all of our reconstructions with our own custom source code or reconstruction code. It's called MAT MRI. So you can feel free to download that and check it out. It's called MAT because we make extensive use of matrix vector operations, and we do that in MATLAB because it's really good at that. And also it has excellent GPU support, and also because that's what I know. So it made a natural fit. So the recon time isn't bad for a 1.5 millimeter resolution spiral. It's about 1 second per slice. I think ScopeI does a little bit better, but we didn't want to take all the time to program in CUDA. So with MATLAB, it's really easy to do it with GPU support. We're also avoiding compiled binary. So this is all just using the MATLAB stuff. So you can just download it and start using it without any compilation at all. All right, so moving on to what we've been up to. So for each project, I'll have a picture of the trainee who's kind of mainly involved in it. You'll see Paul's picture a lot. He's sitting here. He's also looking into postdocs, so keep that in mind. So this project has to do with synchronization delay between the MRI data and the probe data. So as Paul mentioned in his intro, we have these two streams of data coming in, and to get them aligned in time is actually a little bit tricky. With even less than a microsecond of delay, you can end up with large artifacts, and these delays come from things like differing filter delays between the two chains of signal pipes and trigger transit times. And there are pre-scan solutions, but we didn't really want to go that direction because it requires time on the front of your sequence, and also the pulse sequence programming was not trivial, and you'd have to do that for every single sequence that you want to do this with. So we developed a model-based method that just uses the data itself. In short, what you do is you estimate the image first, and this is a convex problem. It has a global minimum, and then from that you can actually recast the problem as another convex problem to estimate the delay. So you go back and forth between those, and we found that it actually ends up converging quite well for both EPI and spiral. Before you do that, this is an example with EPI. You can see there's a lot of ghosting artifacts. And then afterwards, you end up with this. And, I mean, we've been using this now for several years for all of our spiral scans and have never had any issues at all. So it seems to find the delay every time. So another project that we have been working on, or that we worked on, was a transmit receive with integrated field probe. So this is Kyle Gilbert. He's our main RF engineer at the CFMM, very talented. So we purchased field probes, so that was great, woo! But then they didn't fit. You can see that we have this little bit of space at the top. The clearance there is maybe less than a couple millimeters actually, which does not accommodate a field probe. But even if we could fit the field probes, we really wouldn't want to put them way out there anyways. If you put the probes right against the boreliner like that, you're way outside the linear region of this head gradient. So it's really not measuring stuff that's in line with what's happening near the center of the magnet where things are linear. So we built a new coil. So Kyle did a bunch of work there building a coil. You can see that there's 8 transmit elements, a mix of dipoles and loops, and then we had 32 receive elements inside, and then the probes are distributed throughout that here. So we found that there's really, on the RF side, we found that inserting the probes had basically no impact on the RF transmit receive characteristics. So the B1 plus efficiency, the receiver noise correlation, SNR was all great before and after the probes were inserted. On the field probe side, we did find that their lifetimes were slightly shorter after integration, but still for our spiral readouts and EPI readouts, it was still long enough. So we didn't have any issues there. This was actually covered by MRI highlights because we have all, in part because we have all the CAD drawings and everything online on this, and you can find that at the CFMM's website. So check it out if you want to try and build something similar. And then maybe a year after we came out with this, I think Scope released their 17 product. So there's also that option. All right, so this project is related to what I alluded to on the last slide, where I said if your probes are too far away and outside the linear region, you're going to have problems. So even though we had the probes as close as we could to the center of the gradient, we still are outside of the linear region of that head-only gradient coil. So the linear region is only 20 centimeters. And all of our probes were outside, some more than others. So we were really excited to have this coil built, and then we did our first recon, and you can see that it just looked like garbage. So we had 16 probes and 16 basis functions. This isn't supposed to be an FA map. It doesn't really look like it. But luckily, if you go down to fit with fewer basis functions, you actually end up with an overdetermined set of equations, and it's a little less sensitive to errors because it's overdetermined. We still weren't that happy with this. The FA in the gray matter looks higher than it should. It looks noisier than it should. I don't have EPI here for comparison, but we knew it wasn't looking quite as good as it should. So together with Paul, we developed a new algorithm to correct for this. So, whoops. Oh yeah, but before I go into that, I should give you guys a review about expanded encoding. I'm sure most of you know what that is, but here I'm talking about third order and second order, so let me just take a little sidebar to explain what I mean. So the traditional model of encoding is you have some frequency changes, that's a DC term, and then you have linear terms which vary with X, Y, and Z, Z, not Z. And these are your gradients, basically, that you apply. So this traditional model we're all familiar with. These gradients encode you in K-space. The expanded model just expands this to include higher spatial orders. So you can see there's X, Y, Y, Z, and higher orders. You can go up to third order as well. And so that's what I'm talking about when I say third order and second order fits. All right, so back to this. We have second order, we weren't too happy. So we developed a new algorithm. So you can see with our new algorithm, which is magic, we have 16 probes and 9 basis functions, and you can see that FA map looks quite a lot better. So you can tell because it's darker in the gray matter than it was, it's less noisy, and just to compare between what we had just with the vanilla scope kind of method of calculating the K coefficients to our algorithm looks like that. So now I can give you some insight into what the magic actually was. So the problem here is that the field probes that are farther from isocenter, they're sampling really high spatial orders of variation. And those actually project down to lower spatial orders when you're not fitting with enough coefficients or with enough probes. So that causes, the errors are in the 0th and first order terms, not in the higher order terms. And when you have errors in the 0th order term, it creates big issues in your recon. So this is just like a little cartoon to show what I'm talking about. So you have, this is an example of where you have something fairly linear, and then it wows out to crazy things when you get outside of your linear region. And we're imagining that you have some probes just some close to the linear region, but then some far away. So then you try to fit that with a second order fit, and you can see that near the center of the field of view, or this near isocenter, things are really have high error, which is not what you want. Of course, if you do a linear fit, it looks a little bit better. And that's why when we went from third order to second order, it went a little better. So then, so recognizing this, we thought, well, when you're doing those lower orders, you might as well do a weighted least squares and weight those probes that are farther from isocenter less in your fit. And that'll help you get a little bit better. So that's what's happening here. So that's a pretty simple solution. And then what we did from there is realize that once you have, I didn't actually show it on this plot because it's getting too busy. But once you have this linear fit, you can take the residual of that fit and then apply only the second order terms, fit only the second order terms to that residual to get a little bit better. So you can still get up to those higher orders in this stepwise fashion. So when you do that, we ended up finding that the, sorry, there's like a, there we go. There was like a German message that popped up and I just clicked yes. Or no.
That might restart it because that's our managed IT solution.
Okay, well, we'll see what
We'll find
happens. Or was it no? I don't know, I clicked something. So it seems like it's not restarted. So this is, as we go, the best, this is a quantitative analysis with phantom, and we took a silicon oil phantom that has almost no diffusion. And then you can determine errors by comparing the diffusion weighted images to the non-diffusion weighted image, because they have different eddy currents, but basically no diffusion, so you should have the same signal. And we get the least error when we're using our new algorithm with second order fits. If we tried to go to third order, basically you're not really over-determined anymore and you're kind of reintroducing errors. So you want to still maintain more equations than unknowns. And we also tried just removing the probes that were farthest away from isocenter, just to see if just killing them helps, but that always made things worse. So those really distal field probes were still providing useful information, but we just needed to weight it less. And then also, this is just looking as we had a couple of things. So the stepwise thing that I mentioned, there's also weighted least squares. And then there's another part of the algorithm, which I won't go into here, because it's difficult to explain in a short amount of time, is the full correction. And you can see also that these standard deviations are getting smaller with our correction. And this is actually the standard deviation over all the diffusion directions. So the correction's also making things more consistent across directions, which is really important for FA. If there's any sort of systematic error across different directions, that shows up as low FAs becoming higher. All right, so moving on. So this project here, this was done by Gab and Paul. So this method, we're looking at how do we regularize our fits. So far in the literature, before we did this work, all of the expanded encoding reconstructions I could find anyway were just using conjugate grading method, but they weren't letting it converge. They were just stopping early. So when you do that, you're actually if you let it converge all the way, you would be solving this. You'd be finding the X that minimizes this cost function, where B is your data and A is your encoding. But when you do early stopping, you're not solving that. You're solving something else, but it's a kind of implicit form of regularization. You're not doing something explicit there. So we thought probably it makes more sense to use an explicit regularization compared to just stopping early. And we went with the wavelet regularization because it has nice properties. We know that our images should be sparse in the wavelet domain, so we might as well use this. And also spirals, they have quite the point spread function doesn't have well-defined peaks, so it might even be kind of decent for compressed sensing. So the questions we had then is first of all, does the wavelet regularization actually perform better than early stopping for spirals anyhow, which is our main interest? And if so, how much does it compare to the benefits of expanded encoding? So we know going to these higher spatial orders are supposed to help. But how much does that help compared to other things we know, just to get a feel for what's actually important in our recons. So these are some example images. You have fractional anisotropy maps again, and we're always using these because they're really sensitive to errors. And you have early stopping on the top and compressed sensing on the bottom, so that's with the wavelet regularization. And you can see it really does clean up the noise, especially when you have high acceleration rates. So this is 5x acceleration, uniform density spiral with 1.1 in plane resolution. And there are still some artifacts remaining when you go that hard, but for the 1.5 millimeter with 4x, it actually looks really nice. And then this plot is just showing quantitatively how much error reduction you have with both compressed sensing and expanded encoding. It's kind of busy, so I'm just gonna throw some arrows up there to make it more clear. So down at the lower acceleration factors, you get this decrease in error from expanded encoding. At the higher acceleration factors, you get this decrease in error from compressed sensing. And then at middling acceleration factors, which for spiral I'd say is 3 to 4, you get about an equal contribution from both. And this bottom line here with the least error is when you combine the two approaches. So the reason this happens is when you have a low acceleration factor, you have a long readout, there's lots of time for phase errors to build up from your higher order modes. And if you're not correcting for those phase errors, they're going to create artifacts. But if you have, but these ones actually have high SNR, so adding in wavelet regularization doesn't really help that much. Over here at high acceleration factors, you have almost no time for phase errors to build up. So expanded encoding doesn't make a huge improvement there. But you have a lot of noise because it's low SNR, so that's where compressed sensing starts to help. Right, and then this is kind of the last published thing that I'll talk about, and this is more of an application. So far it's just been all solving problems, trying to get the best images possible. Here we're actually using the scope system to help us out with something a little different. For diffusion MRI, I'm sure many of you are familiar with FSL eddy, that presumes that you have time constant eddy currents. So they're basically really long time constants so that when you get to your readout, it doesn't change over time. And that causes a linear variation in K, in your K-space coefficients when it's like that. So FSL eddy can correct this thing on the left really well because that's the assumption that it makes. But we found when we were using advanced diffusion preparations that really push the gradients hard with multiple oscillations that go from full negative to full positive gradients, you end up having this time dependence. And it's hard to get rid of that even with a really good precompensation tuning. So this is what we're trying to correct. So we thought it would be useful to have a retrospective algorithm that accounts for the eddy current delays without needing a scope system. So this is for people that don't have a scope system, but they want to correct for this. So we developed an algorithm that's a lot like FSL eddy, but it has an extra degree of freedom to model time varying eddy currents. So the way we use the scope field probes here is just to validate the algorithm. So you can see the black line is actually the ground truth scope measurement. And then the dotted line is what our algorithm is able to determine from the data itself in a very similar way as FSL. And then the blue dashed line is what you get if you just used the linear approximation. And then, so down here is our new algorithm. So it does decrease the error relative to FSL. This was actually us implementing kind of something similar to the FSL method ourselves, just to make sure that we're comparing apples to apples. So FSL and our method were similar as we expected, but then this is now the higher order model that we developed, which decreases errors, but still a nod to field monitoring. That still gives the best approach because there's fewer assumptions. So getting those higher orders in still decreased the errors a little bit. All right. So that's just kind of an overview of stuff that we've been up to over the last few years, and now I'll talk about some stuff that we're doing now. So now we're moving towards a little bit of things more on the applied side. Something I'm very interested for diffusion MRI is microscopic fractional anisotropy. So this is different from the fractional anisotropy maps I've been showing up till now. It's a new parameter, and I'll just explain how we get this. So traditional diffusion MRI, what most people are used to, sensitizes with diffusion along a single direction at a time. So it has this linear sensitization. But you can also perform sensitization that's equal in all directions. The kind of simplest way to do this conceptually would be all in a single shot. You do a bipolar pair of gradients on X. After that's done, you do a bipolar pair on Y. After that's done, you do a bipolar pair on Z. And you do that all in a single shot. And then there's ways to collapse that down and make it more time efficient by having gradients on simultaneously. But at the end of the day, you have this sensitization in all directions in a single shot. And it turns out if you take all of those linear encodings and just take the average signal over all the directions, you end up with a different signal compared to if you have the encoding in all directions in a single shot. And that difference is related to the presence of anisotropic structures. So the difference between the linear tensor encoding and spherical tensor encoding is related to the microscopic fractional anisotropy. So it gives a measurement a lot like fractional anisotropy, but we go about it in a whole totally different way. We're not fitting a tensor at all. We're taking actually the mean of signals over all the directions and then looking at differences. And then the thing that's important about this is that it's immune to crossing fibers. So in the methods where you use a tensor, if you have a voxel with a populations of fibers going in different directions, then that decreases your FA. But in this one, that has no effect on the micro FA. So I'll just show that more here. So on the left side is FA and on the right side is micro FA. And you can tell right away that the contrast is much more flat than FA. It looks more like a T2 weighted image or something, or a T1 weighted image. And this yellow circle shows where you have darkening of your FA because of crossing fibers. But in micro FA, you don't get that. And then this is just shown on the cartoon on the right. So if you have a voxel where all the fibers are aligned, your FA and micro FA agree. But if you have a voxel where the fibers are all incoherently aligned, your FA is reduced. Here, if they're perfectly distributed in all directions, your FA becomes 0. So with FA alone, you wouldn't be able to distinguish between voxel B or voxel C. But micro FA is still 1 for voxel B, and but then it becomes 0 for voxel C. So we're interested in microstructure, not macrostructure. The problem with FA is that it's conflating the two. It's mixing this macrostructure arrangement with microstructure. So micro FA is useful to help distinguish between those. Okay, so why are we interested in spiral? So one of the things we're interested in with micro FA is looking at combined micro FA and relaxometry. So the main idea here is that some tissue components have longer T2s than others. So I'm talking about the microscopic tissue components, like different cell types or different cell features. And if you use a really long TE, you're basically filtering out the features that have short T2s. So, and then if you compare that to a short TE, then you can kind of isolate those features alone. So it's a way to change your microstructural specificity. And people have shown that this can happen with mean diffusivity, and we're asking the question, how is micro FA impacted by this sort of thing? But this is really difficult to examine because to do that spherical tensor encoding requires a really long echo time. So we want to reduce our echo time with spiral so that we can actually investigate this. And this is just really preliminary results. This is on the left-hand side this is single shot spiral micro FA with a TE of 76 milliseconds. If we had EPI, our minimum TE is something like 94 milliseconds. So we're able to get down to 76, and then we're looking at as we go up to 106. If you really squint, you can maybe see that it looks like the contrast is a little bit different, but just a quick ROI measurement in this subject in the thalamus, you can see that the micro FA actually is decreasing by something like 15% in the gray matter. In the white matter, it's not really changing much at all. So you get a little bit more gray-white matter contrast at the longer echo time. So this is just one subject. Farah up in the corner there is scanning more subjects, and we're going to look at this a bit more detail, maybe do some modeling, and from there. Another thing we're working on is simultaneous multi-slice with spiral. Because spiral, I gave all those nice plots about the SNR benefits of spiral, but it's kind of useless if you don't do simultaneous multi-slice because of SNR efficiency. So if you can just in the same amount of time, acquire 2 slices at once for little S&R cost with EPI, then really, and you can't do that with spiral, EPI still usually wins, unless you're doing really high resolution at 17. So we want to get this working well. So just to give some background about simultaneous multi-slice, so you should have some variation in KZ to reduce the G factor. So what this basically does is it makes your encoding matrix better conditioned. So this is done with CAIPI by having your phase vary from line of K-space to line of K-space. And what this does is it causes your different slices to be shifted in the field of view so that they're not overlapping as much. When you look at K-space for this example, it's just 2 planes in K-space. So you have KX and KY doing your normal grid, and then you have 2 of those for 2 slices. Now, when we look at this for non-Cartesian, so this was done with concentric ring back in 2016, where you have, again, multiple planes of slices, or sorry, multiple planes in K-space. And more recently, for Maria Engel, you have T-hex, which is still, when you do it, it's kind of spirals in plane, but when you look perpendicular, it makes this nice sort of grid-like pattern. And this was designed more so for full 3D acquisitions, but they recently applied it to simultaneous multi-slice as well. And you can see here they're adding blips to like nicely go down to different grid spacings. All right, so in the meantime, we've been developing our own method. We're calling it Lotus SMS. So that stands for lateral oscillations to undersample spiral SMS. The goal here, again, was to have efficient KZ coverage, and we want to make sure we're maximizing slew and gradients to do this in the most efficiently possible. We don't want to pay a price in terms of our readout length to do this. We also want synergy with compressed sensing. We recently found that doing wavelet regularization helps, even with just a normal spiral. But now we're talking about KZ, we actually have another degree of freedom to start designing trajectories that might actually be even better for compressed sensing. They could be more pseudo-random, which should hopefully help with compressed sensing. So yeah, here's what we came up with. There's spiral, and there's Lotus SMS. Wow. But then when we look at it in 3D, it looks like this. So the spiral is just a plane in KX, KY, and then KZ there's nothing happening for a normal spiral. And then Lotus SMS kind of has this wild behavior. So it's starting to look somewhat pseudo-random. Something to point out is that when we did so this was using Pipe's algorithm for keeping maximum slew or maximum gradient the whole time. And then we just added in these KZ oscillations. But at the end of the day, for this particular example, the readout duration was exactly the same for both. And that's because the KZ that you need for multi-slice is really small. Our slices are separated by a lot. So when it's only 1% of KX and KY, and you end up with almost no hit on your readout design when you're just adding these really tiny oscillations on KZ. What this looks like when you have the gradients and K-space. So you can see that we now have this slightly oscillating gradient. So it's really small compared to GX and GY. And then just down here, zooming in on the Z component. So you can see these really small oscillations starting at only 1 millitesla per meter, and then dying down to like a fraction of a Tesla per meter, or millitesla per meter. And then that's pretty constant in K-space in terms of magnitude. And then the main kind of design feature is that we make sure the zero crossings of KZ are based on some sort of golden ratio to make it pseudo-random. So this is showing where KZ crosses 0. So it's kind of randomly distributed so that you get a nice point spread function that should be good for compressed sensing. Another feature with this is it's really synergistic with variable density. It doesn't really matter how your density is varying out in the radial direction, because the zero crossings are all determined by your polar angle. So you just keep doing that. So this is just a quick example of what we've acquired with this. So this is a 1.2 millimeter isotropic micro FA scan at 3T. We acquired in the axial direction, so this is showing perpendicular to the slice direction. We did a full brain scan in 15 minutes with 3x SMS and 3x in-plane acceleration. It had some variable density, so the net acceleration was something like 8x. But we're seeing not really much hint of artifacts at all, even with this high acceleration rate. And this isn't even with compressed sensing yet. This was just using the vanilla model-based recon with conjugate gradient method. So now moving forward, that's what we're going to investigate. We're going to look at how well does this actually work for compressed sensing? Does it improve things with this trajectory over others? So that's what we're working on now. So we're at least happy that we get images, and now we'll see how good the trajectory actually is for compressed sensing. And then another thing we're working on, Paul's working on this, and this is just a little sneak preview. Paul has a pitch and poster at the CMRR workshop after this, so please go talk to him about this later. But the motivation here is basically you can only fit as many basis functions as you have probes. And we saw this earlier in my talk where when we had 16 basis functions and 16 probes, we ended up with garbage images. So we're trying to look at, is there a more compact way to define your basis functions? Or is spherical harmonics truly the best way to define your basis functions? And the solution we came up with is to basically find linear combinations of spherical harmonic basis functions that most compactly describe the eddy current spatial modes on your particular system. So this is a lot like coil compression. We actually took our coil compression code and just applied that to fitting of the basis functions. And these are some preliminary results. So this is on our 7T where things get crazy and the higher orders have a bad impact. So a first order fit, it's not so great. The second order fit actually is still very blurry. But and the third order fit is garbage. And again, this is just in 1 DWI. And you can see that, so here it looks like it's getting worse as you go to higher orders. But that's because we're using spherical harmonics that don't actually describe our system well. And those just blow up when you're trying to fit with a small number of probes. So now this is a compressed fourth order fit. So we took our probes, we found, so fourth order requires 25 basis functions. We collapsed that down to a total of 9 basis functions and found that pretty accurately described our system. So that's the same number as basis functions as a second order fit. So we're now kind of comparing apples to apples. But you can see that we get a much better fit with this one. So yeah, go ahead and look at Paul's talk and poster and find out more details from him. Okay, so I'll just finish with some outlook on where I think it'd be interesting to go moving forward. So one thing is reconstruction time. I know this example is using our code, and I think Scope I is probably a little bit faster. But nevertheless, I think it's still a problem that I think we need to think of solutions besides just brute force coding better. So I think when you think about a scan that has a whole bunch of slices, the difference in the encoding matrix is not that different from slice to slice. It gets to steady state pretty quickly. So I imagine there must be ways to take advantage of that fact in your recon to speed things up. So I think that's something that we should be looking at so that we can actually do online reconstructions. Another thing that I'm interested in is motion. So concurrent monitoring. So those of you who are familiar with this, you put the person in the scanner, and the very first step when you want to do a scope monitored scan is you do a calibration scan. So what does this calibration scan do? It determines the location of your probes in space. It also determines a field offset at each probe. And you have to subtract off that field offset to get accurate K-coefficient estimations. As soon as the person moves their head a little bit, the field offset changes. So I feel like that is probably causing errors, but we don't know how much. So I think we need to investigate how much error that causes. Also, is your B0 map still valid? How much error from the motion are you getting in the B0 map? And I mean, so far, probably most scans, at least in my lab, it's all been grad students that just go and fall asleep in the scanner. If you have a patient in there, I think you might end up with inexplicably worse image quality, but maybe it's from motion. Also, workflow is always improving, but I think it still needs more improvement. Something that we've tried to do is use high density connections, and I think the new scope coils do that too. It'd be great to have integrated reconstructions. The V0 eddy current compensation is still a thorn in my side. I'd love to talk to people here about how they're doing it and use better approaches for that. So I think we need to work on better workflow. Data management is interesting. So if you have that 1.2 millimeter isotropic diffusion MRI scan that I showed, it was a 50-minute scan, and even with 8x undersampling, it was 58 gigabytes in total for your MR raw data and your multi-channel field probe data. So it's just a massive amount of data. Once you do the whole recon, that goes down to 1 gigabyte. And just food for thought, carbon footprint. That recon took 10 hours on a NVIDIA 4090, which is 450 watts. That's 4.5 kilowatt hours, which is 1.9 kilograms of CO2 or a liter of gasoline in your car. Okay, so that's it. So I just want to mention the collaborators. Ravi, who's here, that was with the compressed sensing work and the building the coil, that was in collaboration with Ravi and Kyle. Adam Kerr, I had some great discussions with him at the scope meeting last year, which helped us come up with the basis function compression technique. Camille, we've spoken with a lot about various ideas. And then my trainees, Paul, you saw Paul's picture a lot, so it's going to be an enormous blow to my lab when he graduates next summer. But we have some new trainees now that are going to be doing development on the scope system now. So we should be able to maintain some things. So that's it. Thank you all for your attention.